Greetings, everyone! Welcome to our October Impact Spotlights event. If you were with us last month for our Smart Agriculture event, you will know that this is our free virtual monthly event celebrating our Hackster community, along with the sustainability projects that they're building and the technologies that they use to make that happen. If you haven't seen last month's event, then go check it out. It's on YouTube now. We're going to drop a bunch of links in at the end of this event. We'll put them in the link in the description of this video later as well. If you're watching the recording, you can just scroll down and check them out. But if you're here with us now, I want you to stay focused. So we'll drop those in at the end. You can also sign up for our newsletter via the splash page that you used to get here, and you'll be notified about future events, as well as the webinars that are coming up and all the projects that we're going to cover here today. Okay. So today we are excited to bring you presentations on the theme of smart energy storage. And we've got a couple of different members presenting. I'm also going to be sharing one of my own projects, which is very exciting to me. So this topic is near and dear to my heart. This month's topic is sponsored by Arduino Pro and by Avnet. So we're going to have a couple of webinars coming up with them because they have independent investment in this topic, and they're going to be sharing some really cool techniques and tools with you. So we'll have a little bit more about that later on. First up, we're going to have a message from our director, Ben Strawn, who's going to share a little bit more about those webinars, our topic, and why we're so excited to bring this to you today. All right, take it away, Ben.
Hey, welcome everybody to this month's Hackster Impact Spotlights. Wherever you are in the world, I want to say good morning, or good evening, or good afternoon. My name is Ben Strahan, the director of Hackster. And today we're going to be focusing on smart energy storage. I have to admit, this was a topic that I didn't know much about. From my perspective, the innovation was happening in the area of electric vehicles, where maybe we were working with different materials that were more sustainable, maybe lighter materials, maybe materials that will give us extended range in the same footprint. That was the extent of my knowledge. But as we studied for this month's session, I was fascinated with all the innovation happening in the field. And so today, I'm excited to feature some of those stories from the industry and from the community. Now, this might be the first time that we cover this topic, but it won't be the last. In fact, there was so much innovation in the space that we're going to be planning further sessions around this topic. There's fascinating technology like gravity batteries and elemental batteries. Just amazing stuff to me. And so I'm excited to go on this journey with you and learn more. Speaking of the journey and learning more, we have two great sponsors. By supporting them, you support us. And today, one of them is Avnet. They have a whole series of content that's coming up around smart energy storage. So if you want to go a deeper dive, you'll be introduced to the field application engineers and the system architects and the businesses that are driving innovation in the space. Consider signing up for that series of webinars. Also, a name that you're familiar with, Arduino. They actually have a whole team that is dedicated to Arduino Pro, which are commercial and enterprise solutions featuring the technology that everyone knows and loves. They're fascinating, and they're driving so much innovation in the space that they came on board to tell their story. So they're going to have an upcoming webinar come up as well. If either of those opportunities sound fascinating to you, please reach out, sign up for them. That'd be fantastic. Also, of those from the community that we're featuring today, please interact with them, ask questions, whether you're streaming on YouTube or LinkedIn or natively inside of our app. I want to thank you so much for being here and participating. We can't do this without you. And so again, thank you for supporting this planet. Thank you for supporting Hackster. Thank you for being here today, and enjoy. Bye-bye, everybody.
Yeah, Ben, everybody. Ben is our awesome director, and I'm really excited about all the cool stuff that we've got coming up. So, as mentioned before, be sure to stick around for links. You can check out our splash page to be notified for when we send out the follow-up email with links to the different projects and these upcoming webinars. And then also we'll be dropping them in the chat at the end of this session. Also be sure, as Ben mentioned, to drop your questions and comments in the chat. We don't have everyone live here today, but I will be live, and we've got Hackster team members on the job. So if you've got any questions, drop them in there. All right, so without further ado, let's dive into today's spotlights. Our first one comes from Kevin, who is sharing Volt Valet, which is a way of converting any EV charger to be smart. I'm going to get rid of our banner here and then take it away, Kevin.
It's Kevin Leffler, and today I'll be sharing my project Volt Valet, Make Any EV Charger Smart. It took second place in the Microchip The Future of Resilience contest on Hackster.io and addresses a significant problem in maintaining tomorrow's electric vehicle or EV infrastructure. A quick introduction about me. I'm a cyber software engineer from Denver, Colorado, USA. I'm an electric vehicle and roller coaster enthusiast. I own an EV that I love, and I'm working on building my own electric motorcycle, perhaps to be documented in a future Hackster write-up. The picture on the right is me at my favorite place, Cedar Point, an amusement park in Ohio. Now, if you're an EV driver, you are undoubtedly familiar with planning longer drives and errands using various apps like Plug, Share, ChargePoint, etc. that aggregate where EV chargers are located and if they're working or not. Many cities are rolling out EV chargers at places like parks, community centers, libraries, which is awesome and commendable. However, if you're an EV driver, you also know a recurring issue that occurs, especially with chargers that aren't part of big national networks. You pull up and discover that the charger is faulted, errored out, is off, and now you have to scramble to find somewhere else to charge up. This isn't to place blame on cities with limited resources. Many of them choose solutions like Clipper Creek and Grizzly chargers, which are excellent hardware, but unnetworked, and it isn't anyone's primary job to maintain and monitor them. If you're from Denver, a good example is a set of EV chargers in the basement of the Museum of Nature and Science. These aren't your typical ChargePoint, Shell, EVgo type chargers. Often all these chargers need in terms of maintenance is a restart or for a breaker to get flipped. What if these chargers could be cheaply retrofitted to send someone an alert that the charger needs maintenance? The small device on the right is a Volt Valet, and that's exactly what it does. It's a tiny cellular modem and a special feather wing board that sits on top that can interface directly with an EV charger. Let's explore how. At the core of this project is the microchipped AVR IoT mini cellular development kit. It is compatible with Adafruit's feather wing form factor. I'll discuss how we will build the feather wing that will let us perform anomaly detection and what's called the control pilot signal from the standard J1772 charger. Pictured here is my personal network charger I use my Volt Valet with. We will also discuss how Volt Valet is a one-click deployable cloud solution, which the device talks to over cellular to send you emails or SMS text messages indicating that there are problems with your charger. Here's a bill of materials. This is also available on the Volt Valet project page in Hackster.io with links. Parts are also photographed there on the right. You of course need your microchip cellular development kit. We will assemble the feather wing on an Adafruit feather wing proto board. I have a link on my project page to an excellent J1772 inlet with a charging cable will dock with, and they'll give you access to the full wire harness with labeled wires corresponding to each pin on the charging cable. You're going to need some standard diodes and resistors, as well as a terminal block where we'll connect those J1772 wires. You'll also need to do a little simple through-hole soldering. The cloud software deploys to Amazon Web Services, so you'll need an account for Amazon's cloud. And if you'd like to look at and measure the control pilot signal from the charger yourself, you'll need to optionally set up an oscilloscope. Now, the J1772 charger standard is ubiquitous. These connectors are everywhere. You've probably seen them in parking lots and home garages. They use pulse width modulation or PWM, which is getting familiar to electronics hobbyists. And that's used for the signal emitted from the control pilot pin showed there on the right. You can also see the pins you'd expect for ground and power shown there. And also on the idea of Volt Valet is the normal PWM signal that gets emitted changes the software as the charger enters anomalous modes and drops the rate of things it can charge. This signal is actually emitted to negotiate a charging rate with the vehicle, as well as to indicate if a charger is connected to a vehicle and a few other states. So what's actually communicated by that signal is what the charger thinks it can output. And this is going to change based on the weather, hardware faults, etc. It'll also tell you if the device is off. Of course, it's very well understood and easy to measure with a microcontroller. So here we have the inlet and the wire harness connected to all those pins. Users will dock their charger when not in use with this, And then Volt Valet can measure and monitor the charger to make sure that it's working. We're going to connect some probes to the control pilot wire, that green one, into ground. Also going to connect a small load of about 880 ohms to simulate the load for a car where it starts charging. We'll then connect the EV charger and be careful with the remaining wires and pins since they are now connected to a live charger. This particular kit linked on my Hackster.io write-up has great labeling and color coding for all those wires and pins. Here we see the expected 1 kilohertz square wave for the pilot signal. You'll also notice that to peak, we've got about 24 volts here, which is not suitable for reading with a microcontroller. So what we're going to do is the circuit in this wiring diagram is a diode clipper. We're going to take that square wave, trim it down to about 2 volts so that we can still read the actual square wave, but it's suitable for reading with our microcontroller. Here we have that feather wing that we assembled connected to the inlet, as well as to a couple probes, and then we see the trimmed square wave on the oscilloscope. Now, the terminal blocks at the end, you'll notice, is where the control pilot and ground wires go in. Lets us secure them for a nice, secure connection. Now, what do we do with that PWM signal? We're going to take a software module written by this event sponsor, Arduino, and we're going to build an anomaly detector. K-nearest neighbors, or KNN, is a powerful algorithm where you can imagine drawing a circle around a set of points you want to consider your expected state, shown in the art on the right. And any point outside your circle is an anomaly. These anomalies may correspond to higher or lower charging rates than expected, a charger being off, fault. But most importantly, using a KNN, we don't have to hard code these different kinds of scenarios. It's much more flexible and adaptive than a series of if-else statements, and is a sort of primitive for machine learning. So we'll measure the PWM signal on a microchip board, check it's in our expected circle. And if not, we're going to emit a message which hopefully will be received by a helpful city employee or even yourself. Now, how will we do that? The way we will emit this message is with a rather simple cloud architecture shown in this architecture diagram. These, of course, correspond to different Amazon cloud services. Microchip board will hit a RESTful API, which our cloud infrastructure deploys, which will then use Amazon's simple notification service to send an email or an SMS. You can swap this out using the GUI on Amazon Cloud's website. You don't have to understand what every block of this diagram does, since the way we're going to deploy it is actually by clicking this launch stack button either on the Hackster.io write-up for Volt Valet or on the repo, which is hosted on GitHub. And what this does is it takes the CloudFormation document in the repo and discussed in the Hackster.io write-up and deploys it to your Amazon cloud for you. So there's no cloud expertise or any sort of networking or infrastructure as code experience needed to deploy a Volt Valet. So what those emails will look like is shown here. So if you named your deployment something like community center or a police station to correspond with where your charger is perhaps deployed, you'll start receiving status updates in your email. If you subscribe to the Charger Simple notification service topic, you'll get an email saying subscribe to this charger's topic. That is a kind of like a newsletter for different updates about a given charger. And this would also happen over SMS if you choose that option instead. So here we have the final demonstration where I'm going to take the portable charger that came with my car. I've got it plugged into the wall here in my lab. I'm going to disconnect it from power, simulating a power loss to the charger. And there'll be a quick cut because I don't want to show you my whole inbox. And you'll see I got an email 0 minutes ago indicating that the charger experienced a problem. Now for next steps, I want to expand the tutorial to include the North American Charging System, or NACS. If you're a Tesla driver or Tesla user, you'll recognize this as Tesla's charging standard. This actually uses the same pinout as J1772, and the pilot signal is the same, so this will all connect and work with the Volt Valet the same way. I've just been receiving some great feedback on my Hackster.io profile asking if this will work, and it turns out that yes, it does. I would like to write some code for a learning mode. There's a lot of manual steps in my write-up about how you get values to set up your KNN. I'd like instead for this to be a smart plug in the charger, have the code learn itself what the steady or normal state is for your charger, and then identify anomalies. And finally, I'm a 3D printer enthusiast. The nice orange enclosure down there is for a separate Halloween project, but I love to make a 3D printable enclosure and cradle to make it very clear to users that you should dock the charger with Volt Valet when you're done using it so we can monitor if that charger is working or not. I'd like to thank you for watching this video. I'd also like to encourage you to visit my Hackster.io page about Volt Valet to get some specific details about how to build one. You can also get a link or go directly from this link to the repo on GitHub and look at the code and the CloudFormation template, which defines the architecture for the cloud infrastructure, as well as my socials. And I'd like to wish you a happy Halloween, and thank you for listening.
Happy Halloween to you too, Kevin. Thanks for joining us. It's true. I'm very excited for that holiday that's coming up in just a few days here next week. All right, so next up we have me. I'm going to be sharing some stuff around the Joule Thief, which is a pre-existing circuit that I'll tell you a little bit about, but I've created a PCB and some example projects with it, and I'm very excited to share because this is one of my favorite circuits, and it just gets me hyped. Okay, so where are my slides? Here we go. All right, so the Joule Thief circuit is a self-oscillating voltage booster or transistor blocking oscillator, or also known, I think, as a Joule ringer, so Joule as in energy, whose most popular form was shared by Z. Koparnik in Everyday Practical Electronics in 1999. Eventually, this iteration was designed and named in 2002 by Big Clive on YouTube. And it integrates a bunch of different cool stuff. So, about me, I am Hackster's pro-creator in residence. I make tutorials, videos, projects, all kinds of cool stuff. And I've been working on this project I call Green EE, which is basically green electronic engineering. It's a directory of resources for people who want to make electronics in a more sustainable way and also make things that are electronic that serve sustainability ends. And so you can see a few of the different goals that I have here. So for example, multi-use PCBs. So creating PCBs that are artful, beautiful, and wearable, so that even if the PCB doesn't initially work, or if you're not using it for anything, you're still not just going to throw it out and it doesn't enter the waste stream because it's an object of art in itself. And we'll see a little bit more about that later. Renewable materials. In these projects, I've used recycled filament and paper, which is a very readily recyclable material, readily available. It's also quite accessible. It's pretty cheap. And then also reclaimed and repaired components that we'll see more about. And the whole goal here is to encourage win-win thinking. There's a misapprehension that things that are sustainable are by nature more ugly, less elegant than things that are solely designed for utility. And I think that we don't need to put up with that. We can have things that are beautiful and sustainable too. All right, so more about this circuit. It incorporates a transistor and a ferrite toroid. And I'm going to, I always mess up this explanation, so I'm actually got a slide about that. But first up, we've got a PCB here that you see, and on the bottom there are a couple of blades or fins that are big contacts that you can attach conductive tape, you can solder things to them, lots of different ways that you can connect an energy source. And basically it enables you to pull the last amounts of power out of a supposedly dead battery. So it's low on voltage and you can't get it to light up an LED. Here's how you can amplify that voltage to get it to turn something on intermittently. So this isn't something you'd want to run a microcontroller off of, for example, but you can run an LED off of it just fine, and it looks like it's on all the time because of persistence of vision. So I did write up a little bit of an explanation. You connect an old low voltage battery. It could be other sizes as well. The whole point is that it's an old one that maybe isn't useful for other stuff and you would otherwise throw away. Pass the small available current through wires that are coiled around a ferrite toroid, aka a little donut shape. And it induces a magnetic field in the toroid, which pushes more current through the circuit, and it builds and builds and builds, and eventually the magnetic field collapses. I believe it's called supersaturation, I could be wrong. And it dumps current through the transistor. It basically forces the gate of the transistor open, and then it all gets dumped through into the LED along with a tiny amount that's still coming through from the battery, lights up the LED for a moment, and then it sort of reverses the entire process. The transistor gate is shut and the cycle repeats. You can see a close-up of the circuit as well. So there's a few rectangles on here that indicate holes. You can see those big copper things that I've labeled fins are above them. There are some holes that you could put conductive tape through if you want to have the battery mounted below, looking from this vantage point. But also you could put them through the center between the two fins if you want to have them aligned outwards, as I've shown here, for example, with this battery. And I'm going to show you now an example that I built with this configuration to convert some LED tea lights that we had at my old house. So someone in my old house had done a project that was really cool that involved about 1 million of these LED tea lights. And I thought it was such a shame that they were just sitting around forever now because no one was going to change out the CR2032 coin cell batteries on these all the time. And also that would be immensely wasteful. But I still didn't have a good solution for rechargeable batteries on my own. So I created this so that I could sort of drain those batteries and light up these LEDs, sort of a win-win situation. And in the future, I can also use rechargeable batteries, no problem. So you can see that we're using just the base PCB along with some hookup wires, an LED. I've got an LED indicator on the base PCB itself, as well as the Tealight has its own LED built into it and has a little flame attachment. I modeled this in Onshape, and then 3D printed it. So we can see the enclosure here. In the top of there goes the Tealight. You sort of do a little bit of zombie hacking, Frankensteining on that to make the wires come through the bottom. And then you see where the PCB goes. And then there's a switch on the left side in that first little shallow well. There's a clip on the right side, which is a little spring attachment to help hold the battery in place, as you see here. So that provides tension so the battery doesn't just fall out of the bottom. And then you've got, I used conductive tape and also sort of some messy solder blobs to create the connection with the battery. You can kind of do whatever you want there. And I hope to make an updated version sometime soon. Again, this was printed with recycled filament, so I think this was PLA, but you can get all kinds of different ones these days, and they look gorgeous. This is, for me, it's a matte sort of mauve purpley color that I really like. Finally, I've got this light up origami LED bouquet, which is something that I built for Valentine's Day, I think last year. And as you can see, it's a bunch of tiny little origami flowers with some LED string lights in it that are powered by the Jewel Thief. And then there's a little switch, which is, instead of being mounted in an enclosure like before, it's mounted externally to this little flower pot. And one thing that I love about this project is that there's so much reuse here. So for example, this flower pot is one that I had broken accidentally, and then I did kintsugi, which is the Japanese art of mending things with gold, so that it has that extra little beautiful flair on that. And this, what's called a wabi-sabi aesthetic, so things that have been sort of damaged or worn through usage. And you can see in the top right there, the way that that's been mended. And then all the little origami flowers that I folded. There's actually a time lapse of assembling this in the project, which you can see linked here. I like that this one, as opposed to the 3D printed ones, is a little bit more crafty for people who want to work with their hands, get more tactile with it. And also it's, you don't have to have a 3D printer. Also, it uses a little bit less energy than 3D printing something. So, as much as I love 3D printers, they do take a lot of energy. You've got to melt all that filament and then extrude it using motors and such. Stepper motors take a bunch of juice, but you can see the sort of guts on the right side here, and those flowers are not exactly faster. I would not say faster, but they do take less energy to put together, and it's fueled by snacks, which is great. So I also wanted to share the method that I use to create these beautiful PCBs. So as I mentioned earlier, one thing that I like about making PCBs is making them wearable and beautiful, so that even if they don't necessarily work, or if they do, they're multi-purpose, and you're not just going to throw them out because they're not particularly working, maybe, or you decided not to keep the project or anything like that. I'm going to keep these around no matter what, and I created a tutorial for how you can create your own hand-drawn PCB designs in KiCad or KiCad I like KiCad because you can say iPad to KiCad, and obviously, why wouldn't you? But anyway, so these are 3 different more PCBs I designed, including a guitar pick one that does work as a functional guitar pick for the Avnet 100 years celebration back in 2021. And yeah, let me see if there's anything that I forgot. I love the Jewel Thief because it's bringing waste energy back. And so as you can see here, I have ideas for more styles in the Halloween theme. I think that a zombie or a Frankenstein or a vampire would all be very appropriate. You've got zombie batteries that you're bringing them back from the dead, etc. The Frankenstein one, maybe that's more about like suspect power sources. I don't know. But the vampire one, you're sort of like sucking the last of the power out of it. Anyway, so next week, I'm actually going to be doing a live stream, hopefully with one of the folks from Oshawa, and get these open source certified. I'm definitely going to be doing it with the companion core and the ESP or Ouija 8266 that you see on the right side there. But I would love to do this one as well. However, given the storied history of this circuit and the fact that this one was refined and named by someone else, I'm kind of wondering what the deal is with attribution on that and whether I can license it as open source. And I'm going to be asking the Oshawa crew that in advance. So if you're curious, just follow us on YouTube and you'll be able to find that, or LinkedIn, or wherever you are. And then also, I would love to do more adaptations and implementations with this, more projects. So like a USB battery charger, maybe. I've seen people do circuits like that where you take this unstable, low power source and then use it to charge a more usable, efficient source. Of course, you're going to lose some more energy in the process because of inefficiency, but it's all free energy anyway. It's stuff that you were going to not use in the first place. And then also supercapacitors. I've been really interested in supercapacitors lately, and we did a recent interview with Sander van de Boer, who's the creator of California Steam and a bunch of really beautiful supercapacitor-based small wearable PCB jewelry, which is not only gorgeous, but also it uses these supercapacitors, which are much more energy efficient, and they can be charged many times over, and they oh, my brain. I'm trying to organize the next thing, actually. So let me just focus on this. So they can be charged many times over. They're more efficient, and also they have a million cycles, so you're not throwing something away every time your device runs down. Thank you so much for listening. I love sharing this stuff with you folks. Feel free to check out my other projects on Hackster. I've also got a page where I've organized them in a different way, so you can see them by like companion bots and wearables and stuff like that, and go follow me if you'd like to see more weird, fun stuff that I do. Cheers. All right, so let's all take a moment to breathe, myself included. I'm going to pull up a slide about our upcoming Arduino Pro webinar that's going to be run by Gunit Singh of Arduino. And I'll talk you through that a little bit. We don't have a presentation, so it'll be pretty quick. And let me just get that up for us. This was the final piece in our planning, so please forgive me for the iffiness. And in the meantime, I'm going to put up our slide. There we go. There we go. All right, so sustainability and impact with Arduino. We'll be hearing from Gunit about, oh, my bad. I thought that it was Gunit Singh. It is Gunit Betty. So sustainability and impact with Arduino. Arduino's sustainability and smart energy storage is going to include all this good stuff, including real-world examples of sustainability solutions in prototyping and production, use cases from AMB Vapor and Optim Motion for environmental monitoring and water treatment, benefits of sub-slab depressurization systems, which I don't even know what that is, and I'm excited to find out, and industrial compressors. an overview of the Arduino Opta Micro PLC and its energy management capabilities, and integration of the Arduino IoT Cloud with hardware for industrial applications. The Opta system is really cool. I've gotten to see a little bit about it, and we're going to be covering some more about that next week, actually, with the Blues Wireless for PLC kit, which also works with the Arduino Opta system. So lots of cool stuff coming up around Opta, around PLCs, and around industrial IoT, relating as well to smart energy storage. So next up, we have our final presentation of the day, which is coming from Mateusz. It is the Matter Energy Harvesting Power Meter, which sounds like the opposite of what most power meters do. So let's have a look. One thing I love about this one actually is that he says his last name means spider, which not every day.
Hi, my name is Mateusz, and I want to present you my project for Hackster.io, and that I can show you today on Impact Spotlights. So firstly, my project is Matter Energy Harvesting Power Meter, but a bit later about it. Firstly, I'm Mateusz Pająk, which means spider in English. I'm a C++ developer, mostly working on embedded systems, on automotive systems, EQ, etc. But I also want to go to aviation systems someday, maybe. In my free time, I like to work with home automation systems like IoT, so such as Zigbee or Matter. Also on robotics, as you can see here, some safety or diagnosis systems, as you can see, and other automation systems like this hydroponic garden prototype. Okay, so a bit more about the project. You can see on the right the prototype for it. This is just pretty much basic power meter that you can use to track power usage in your whole home, or at least on one phase of your home if you have more than one phase. So there are some inspirations regarding this. Firstly, it has to be easy to attach to your installation, so no alternating to electrical installation, as it's pretty much dangerous for inexperienced people. It also requires a license, so you pretty much can't do that anyway, or you will get a fine. So my solution was to create some device that's pretty similar to Philips Hue or some other smart plugs. So for smart plugs, you just take the smart plug and connect it to normal plug that you can just control with Wi-Fi or Zigbee or something like this. Same goes for Philips Hue. Like you can just attach it like normal light bulb, so this is pretty safe compared to working with live voltage on wires. Also, there is not a lot of such energy meters available today. Like I couldn't find anyone, to be honest. I also wanted to make it non-invasive, so you don't need to alter anything. Like you don't need wires, you don't need to track some power supply for it or anything like that. And I also wanted to make use of current transformers, as they don't seem to be a bit popular amongst hobbyists or in home usage overall. So let's start with a bill of materials for the project. So I have used the NRF developer kit from Nordic Semiconductor. It's a pretty good choice for such project, as it's made specifically for wireless communication and low power usage. I have used, of course, the current transformer. This transformer allows me to measure current in the wires without interfering with my current installation. I have used some supercapacitor to act as a battery, so the project can be charged and powered by the supercapacitor. I have also used from the main components the comparator and XOR gate. This is the main body of Barden controller, which a bit later about. Barden resistor which is used as like power dissipation for the system if it doesn't need any more power, and also for measurements. Like you just connect two wires to the both terminals of the resistor and use some ADC system to measure it correctly. And of course, like in every other electronics project, I have used some transistors, diodes, and resistors, mostly for safety systems for current and voltage limiting. I wouldn't list all of the models and types as you can see on the project page or GitHub if you want to dig deeper into this. So, starting from the schematic of this project, you can see the first row is the power management. You have the terminals to the current transformer. You have the full bridge rectifier, as we are working with alternating voltage and current, so we have to rectify it. Of course, you have the voltage clamp. You have to clamp the voltage to specification of your capacitor, as otherwise it would blow up if charged too much. Of course, current clamp for 60 milliamperes, as I can see. It's also required for the supercapacitor, and it has pretty much low charging current, so we have to be safe about it. You have also control systems, like if the charger or border controller needs to be switched off, like the capacitor is charged enough, so this circuit will disable the charging it more. And this transistor works as disable for as a switch for measurements. Like we don't want to have any current in any other part of the project than on the burden resistor, so we have also to disable the charging circuit. And also you can see the capacitor, nothing to say here, this is a battery for the whole project. And on the next row we can see some control logic, like the border control. So this part of the project is, I would say, the most important apart from the microcontroller. Uh, Firstly, it works as a power dissipation system. If we can provide the more power to the capacitor, we have to make an alternative route. So this is this resistor, but also we can enable or disable it if we want to make measurements uh, for the system. Like you can see here, there are two terminals. Those are for comparator. That's you can see here. This pretty much provides us pretty precise current measurements that go to the microcontroller, and also it works as like age bridge for the motors, as this is still alternating current and voltage here, so we have to disable and enable it from both sides of the sine wave. Some boost converter to provide stable voltage to other parts of the system, such as a microcontroller, some voltages, and hysteresis. I will take about it a bit later, as there are some other diagrams for it. Measurements, the XOR gate is not really important, and the power supply for the system, which you can see goes from hysteresis out to the MCU terminals. So let's start from the beginning. How this project works? It has like 5 phases. I will briefly go through all of them. So you have your mains that are wirelessly connected to the current transformer. The current is inducting in the transformer. It goes through the protection circuits, as I stated here, to the charging control, which is the hysteresis and the XOR gate. and to the supercapacitor. Like the charging control is enabled right now, so it charges the supercapacitor. Other parts are disabled right now. And this is the initial state of the project, as we don't provide any other power to the microcontroller. So we have firstly to charge our supercapacitor to provide enough voltage to our development kit. But after it charges a little, we have the uh, low boost, low power boost converter, which kicks in after some threshold voltage, let's say, and it goes to the charging controller, which is the hysteresis. The hysteresis pretty much compares the reference voltage of the low power boost converter to the voltage of the capacitor, and it decides if the microcontrollers should be switched or not. So we have the charging circuit, but after it gets charged enough, the charging controller kicks in, disables the charging control, so the this FET transistor, and it stops charging. The low power boost converter and charging controller enables the MCU, and MCU starts reading the burden resistors voltage, which means we can measure current right now on our systems. But if we don't have any load, like there is no, like everything in the household is disabled, we also have the current transformer, but it doesn't work right now. Like it's active, but it doesn't measure anything. But we have the supercapacitor already charged, so we can continue the measurements until it discharges. Like there is enough time passed between our charges, so and mains didn't kick in at the time, so our supercapacitor got discharged enough, so the charging controller detects discharge via hysteresis circuit and disables the development kit and kicks in the charging control again until it gets charged enough to perform measurements again. Most of the time it shouldn't happen as the main lines in household are pretty busy, but it's a good enough edge case to include it. And that would be it from the diagrams of the system. I guess it's pretty easy, like it charges through supercapacitor. If it's charged enough, it kicks the MCU. The MCU goes from deep sleep into the measurements mode and provides them via Matter interface to your smart home system. So there's not a lot of uh, like logic behind it, and also some edge cases regarding discharging enough to destabilize the microcontroller. So to sum up, there are some problems that I had with my project. First, I didn't have lack of precise measuring equipment, but thanks to the being awarded the reward in the contest for smart home devices from Nordic Semiconductor, I received this power profiler that I intend to use in next iterations of the project. Also, some better oscilloscope would be good for this project, as mine is pretty much cheap and too digital, let's say. I also would need to check for better fitting components like lower power consumption, lower voltage requirements, lower voltage drops, as right now I have used generic components, as I stated in bill of materials. And I think I also would have to work on better optimization of the code, as I was pretty much on deadline for the project. So I had to use what I had, but some deep sleep modes for like periods of measurements and periods of sleep would be good to provide longer time of operation. But I have it included in my next steps, like I would have to measure it with better equipment, replace generic components, try to provide some voltage measurement, as right now the project just measures the current, and it would be good to include voltage measurements so we can just have power measurements in one box, like it should be done. I also want to create a PCB prototype. As you can see, it's a bit of mess of cables, as I made the all of this as separate um, as separate sorry separate components, as you can see on the photo here, because I wanted to test all of them like separately, so I can know that the voltage clamp works correctly, current clamp works correctly, the hysteresis works as expected, etc. So it stayed that way for this time being, but I intend to make a proper PCB prototype with some test spots rather than the mess of wires. And also I would like to test the 3 phases prototype. As you can see, some generic project from the internet. It also includes the current transformers, so it would be good to like recreate the 3-phase prototype from scratch. But I would do it after the PCB prototype and with better components. So that's it from me. Thank you for watching my presentation. I hope you like it. I'm kind of nervous if it comes to such things. Here is you can just copy the link to the project page. Here is my profile on Hackster if you want to see like other projects that I included in photos here and some more. And also some social media links that if you want to add me on LinkedIn and watch my code on GitHub or watch my 3D print models on printables. So thank you very much.
Awesome. Huge thanks to Mateusz for sharing his project. I thought it was really cool that he's using supercapacitors. As I mentioned earlier, I'm all about those these days. I still have no idea how they work, but I'm going to check it out. And I think that projects like this are very inspiring for that reason. Also, we've covered both the Power Profiler Kit 2 and the NRF 7002 from Nordic Semiconductor that he mentioned in there. We've done a bunch of coverage, especially around the NRF 7002 Developer Kit, which you can find on our channels, including a couple of videos. So now, before we share today's links and other info, we have a brief message from Travis at Avnet, who's going to be sharing a bit about the upcoming webinar on the theme of smart energy storage in the age of AI. So take it away.
Hi, everyone. My name is Travis Dossett, and I am the Director of Industrial Sales at Avet Americas. Avnet is excited to be here in support of Hackster's Impact Spotlight on energy storage systems. For those of you in the audience who may be unfamiliar with Avnet, we are a global distributor of semiconductors as well as interconnect, passive, and electromechanical components and solutions. Avnet has over 15,000 employees, including 2,000 plus engineers, spread across 250 locations worldwide, available and eager to help you bring your company's latest project to fruition, just like we do for over 1 million customers each year. Whether it's supply chain or design chain support that you need, Avnet's got you covered, backed by our line card featuring hundreds of supplier partners. In addition to our experienced field sales and engineering teams, we also have dedicated teams at the Americas level to provide an additional layer of support for customers within specific verticals, staffed with experts who can bring you the latest and greatest solutions. For the industrial vertical team, energy storage systems is a major area of focus. Rising energy costs and growing concerns over energy security are driving a surge in the need for energy storage. Energy storage systems are enabling us to add capacity to the grid to support countless applications in residential, commercial, and utility sectors. In support of this focus, Avnet is teaming up with 7 supplier partners to host a 2-day series of webinars on October 29th and 30th entitled Smart Energy Storage in the Age of AI. Join us for 7 sessions across 2 days to hear directly from thought leaders at Infineon, NXP, STMicro, onsemi, Molex, Amphenol, and Digi as they present their respective solutions within the energy storage space. Each session is an hour and will include a presentation as well as a live Q&A with the presenters and Avnet's technical experts. Register now using the link in the description or by scanning the QR code on your screen to gain access to all 7 of these sessions, as well as supplementary materials direct from our supplier partners. If you're unable to attend live, no worries. All of the recordings will be available for on-demand viewing starting 24 hours after the conclusion of the event. Thanks to Hackster for hosting this Impact Spotlight, and thank you, the audience, for tuning in. I hope to see you all at our webinar series next week.
Sweet. I see my illustrious colleagues at Hackster are already sharing the link for this webinar, which you can find at on24.com. So check that out. I really want to shout out my whole team here. So as we wrap up, we've got Katie and Jesslyn from the team who have been complete awesome humans helping make sure that everything runs smoothly today. We've also got Ben and Ginger present on the back end, and of course the whole Hackster team. I'd like to make sure that you check out all the links. So we've got the whole list of links coming up in the chat here, and also you're going to be able to find those on our Impact Spotlights page. So be sure to check out next month's event on November 21st. We're going to be talking about connected health. If you have a project for that, we'd love to see it. We'll also be sending out the links to today's projects, including Volt Valet. We've got the Matter Energy Harvesting Power Meter from Mateusz. We've got my things, including the Joule Thief PCB, the Tealight adapter, the LED Bouquet, and the PCB art tutorial that you saw today. All this stuff and more you can subscribe to via the big red button up here, subscribe to announcements, or you can go check out the next event directly, which is going to be sponsored by Nordic, and you can also check out last month's spotlights as well. So in case you missed our smart agriculture feature, that was really cool, honestly, and we had a bunch of really cool talks. So really looking forward to next month. And as Travis said, thank you all for joining. It's such a pleasure being able to share all these with you. You are our community. We wanted to, actually, Ben is kind of the mastermind behind the whole shifting our impact mission. The current format of Impact, which has gone through actually a few different iterations. We started out with some contests, and then we had a couple of annual events, and now we're doing these monthly free virtual events to make them really accessible to more of our community, both as viewers and also as presenters. We want to really highlight and celebrate the cool stuff that you folks are doing. So we'd love to see what you're doing with Connected Health for next month, but also it's just a delight to be able to bring these to you. So Katie and Jesslyn, I don't know if you'd like to join us now, but feel free to come on screen here. These are the awesome people doing a lot of the technical stuff, writing in the chat, as well as Ginger and Ben, and really helping run the show. Thank you, folks.
Thanks, Alex.
Yeah. Okay.
Thanks, everyone, for joining.
Yeah. Yeah. All right, cool. Without further ado, thank you all for joining again. Thank you again to all of our presenters today, and hack on.